Hey, good morning, everyone. My name is Aparna Ramani. I am the VP of Engineering for Meta's Data Infrastructure team. I'm just super excited to welcome all of you here today to today's Data at Scale event. It's just always great to engage with this community, especially my fellow data geeks. Today, I want to chat about what I think is just the single largest challenge we face together and also the exciting opportunities we have as an industry to rise to it. I want to talk about using data for AI. There is no doubt that AI is bringing incredible positive change to the world. From mRNA sequencing, medical diagnosis, we see this in weather and climate forecasting, we see it in automation and industrial safety, and of course in ranking and recommendation systems, and just so much more. But none of this works without being able to train these systems with, you know, data. And the use of data for AI is growing far faster than it has for analytics, for experimentation, or for monitoring. This inflection point in the middle of this chart is real. We're facing it today, and I bet many people here are seeing this too. So today, I'd love to talk about our approach to overcoming some of these technical challenges that ML brings, and I'd love to share what we've learned so far. The first of which is that demand will always outpace supply. I know that sounds a little extreme, but let me explain why I think so. For one, research in AI is just evolving rapidly. New techniques and models are emerging quickly from all over the industry. For example, scientists at Meta just released the first 175 billion parameter language model to the broader AI research community. And so far, what's interesting is that few of these models seem to require less data. So our infrastructure needs to keep up with this pace of innovation. Second, the AI training lifecycle is highly iterative. We all know that it takes rounds and rounds of experimentation to get good results for ML models. And this puts highly unpredictable ad hoc load on our data infrastructure. These workloads also look very different from what our traditional workloads used to be like. And third, these ML powered systems constantly demand fresh data. Long after a training process has completed, we need to be feeding fresh data back into these models so that our systems can constantly react to the changes in the world around them. If, like me, you watched the Oscar Academy Awards this year, you know that data requirements are neither deterministic nor predictable. Okay, so maybe this sounds a little bit abstract, but for a moment, let's understand what this means in terms of physical infrastructure. This is inside of Meta's new 100% renewable energy data center in Ohio, with the obligatory blue lighting, of course, from Facebook. And this data center is just vast. Each has thousands of GPUs settled in hundreds of racks. But what may be not clear from this photo is that we've had to completely redesign our data centers for AI. For example, we've come up with rack designs that connect thousands of GPUs together to enable very large jobs. And we've had to design faster networking architectures for the high throughput communication across these accelerators. We've even had to come up with new liquid cooling systems to keep these GPUs running optimally. And coolest of all, our hardware software teams are co-designing the training, inference, and algorithms that all have to optimally work on them. Zooming out, we get a sense of the scale involved. These rack configurations are repeated over and over again across each of the data center's many gigantic halls. By the way, one thing that's not shown here is just the long line of trucks that are delivering these hardware components, because at this point, what's interesting is that AI hardware cycles are faster than traditional hardware. It's sort of like a new kind of Moore's law. It's quicker than every 2 years. We get chipsets and machines that are twice as powerful. So this ongoing provisioning of these data centers is continuing. We're never done. And if the scale of one data center seems huge, just wait until you zoom out just one more time, because of course, there were many of these. Over the next few years, we are turning up dozens of similar data centers across the country, around the world. And when I said demand will always outpace supply, it also applies to things like electricity. We're having to make deep investments in renewable energy and technology across the country just to power these data centers sustainably. So, why does ML have this voracious demand? One root cause of this demand is this: the very non-linear relationship between the volume of data provided to a model and the improvements to its performance and accuracy. For example, let's look at this chart from a research paper we published in 2019. It shows the accuracy of the model on the y-axis trained on ImageNet image data as a function of model capacity. First of all, if you look at the x-axis, you'll notice that it's logarithmic. The capacity has to increase more than an order of magnitude to earn a barely 1% increase in accuracy. ImageNet at the time of this experiment had about 14 million samples. But we really wanted to know what happens when you increase the total amount of data to. Well, here are the results from the research running the same model using images from Instagram. And we used about 940 million samples, over 65 times more data. So was it 65 times more accurate? Turns out, not really. We only see a 5% improvement. Now, to be clear, a 5% improvement in accuracy is awesome. This could be business critical, but it's disproportionate to the amount of data we needed to supply for it. And what's interesting is that we see this growth in every dimension. These charts showing data from OpenAI plot test loss against compute, data size, and parameter count. In these charts, down is better accuracy, and to the right is more expensive. And yeah, we need more compute, more data, more parameters to make these models more accurate. And by the way, each of these graphs is on a log-log scale. So here's something else we learned along this journey. Different ML applications need different data optimizations. So we found that when it comes to providing data for ML, there's no such thing as one size fits all. The way that we need to provide data for ranking models, for example, is radically different from what we do for NLP, which is radically different from computer vision, and so on. As an example, let's look at these content understanding models. Models in content understanding process photos, videos, audio, language, and some of these training samples are super large. The data is complex and is often stored as binary blobs. These models are dominated by compute. They have to be run on GPUs in highly parallel fashion. And some of these models have to scale to thousands of GPUs. But since the data interpretation itself doesn't change often, well, a cat is still a cat. Generally, we find that we don't have to retrain these very often. On the other hand, ranking models are dominated by data ingestion. We need to ingest tens of billions of samples at high throughput to keep GPUs busy and learning fast, and they use order of magnitude less compute per training sample compared to a model processing photos or videos. But to get the best results, we have to keep retraining these models every few hours. So already you see the data optimizations we need for these models are fundamentally different. What's also interesting is that the exponential growth in demand for data combined with the challenges brought by this variety of use cases for ML leads us to this realization: that data infra must be redesigned beyond just incremental changes. I mean, we have to innovate in place, but we can't rely on gently iterating on these classic warehouse technologies of the past. Just as an example, when we were much earlier on this journey for ML, we used to read training features in the order that they were written. And this was simply because that's what we used to do in analytics, and we were leveraging the same stack as was for machine learning. But we quickly learned that this was just extremely inefficient. In fact, we were losing about 80% of the I/O. 80% of the I/O was wasted during training. So this was our aha moment, and we needed to redesign just several parts of our infrastructure in more radical ways than what we had envisioned. This included everything from how data is placed, how it's stored, new abstractions for data processing, how we optimize I/O, rethinking developer experiences across analytics and ML. And we realized that it all starts with how we place training data, across our data centers. Our training datasets, as you can imagine, have been growing very fast, and we had to shard them across multiple data centers across the globe. It sounds simple, right? It turns out that cross-region reads at our scale would just saturate the cross-region backbone network. So this required us to create smart data placement and routing algorithms to optimally co-locate training data with compute. Now, this is a very interesting problem. It's almost like playing a game of Tetris because we have to anticipate where a job is going to run at any given time. We have to proactively bin pack data into the right data centers with efficiency. And we also have to route interactive queries to the same data at the same time. Once data was placed next to our training clusters, and once we figured out how to solve that problem, we then needed to make sure that the training clusters were effectively utilized because reading large amounts of data is a prerequisite for training. And so we invested in optimizing storage and I/O for training because unlike traditional warehouse tables, a training table has tens of thousands, even hundreds of thousands of features. And a large part of these features turns out are experimental. Each job is only reading about 20-30% of these features. Our traditional way of storing features used to be in map columns, which ended up with us overreading lots of data, again, wasted I/O. And one cool trick that our teams came up with was to flatten the maps so we could read features selectively and then further optimize by reordering the features based on the usage patterns. We're also building adaptive compression algorithms. We're adding native ML types, quantization. All of this just helps make our systems more efficient for these new kinds of workloads. But it wasn't enough to just redesign our core infrastructure. The profile of our users was changing, and so we needed to think about the dev experiences for this more diverse user base. And historically, we've thought about data scientists and ML engineers preferring Python and notebooks, whereas traditional warehouse users largely being SQL oriented. And what we're seeing is that these roles are really starting to blur. Users want semantically consistent interfaces spanning everything, the whole life cycle, from data prep to training to inference. And so we've done a few things to help with this. One thing we've done is to bring SQL, notebooks, and data visualization experiences together so we can create this sort of superset integrated experience. We've built an open source vectorized evaluation engine, Velox, that spans multiple compute engines that we have at Meta, and it also spans both analytics and machine learning workloads. And we've created this really cool open source tensor-like Python data frame library called Torch Arrow for data pre-processing and deep learning, and this is tightly integrated with PyTorch. Although we've redesigned our data infrastructure to better support ML, the ML models themselves are only as good as the data that powers them. And of course, there's many factors that go into the quality of an ML model, and I want to highlight one of them. Data freshness has a dramatic impact on model quality. Say you're at Disneyland for only a couple of hours and you posted photos next to the Millennium Falcon. Naturally, you're going to be interested in exploring interesting rides and events happening during your time there. So we have a very short time window to let you know about this happy hour with Chewbacca that's happening nearby. So ranking and recommendations have become more real-time in nature, and they need to use the freshest signals that they can get. So how do we help with data infrastructure? We use our streaming systems to create features in minutes or even seconds to make new features available during ranking. So I just talked about our approach to designing infrastructure for ML, generally optimizing for time to impact. But what happens when something goes wrong? Can we detect it? Can we root cause it? Can we fix it quickly? And this brings me to my next point, which is ML adds exponential complexity to observability. If we thought systems monitoring was complex, debugging ML issues adds this whole new set of dimensions. There's just too many possible root causes when something goes wrong. And sometimes it manifests after a very long time. Honestly, we land up dealing with a high percentage of unknown unknowns. When we have an incident, our teams have to start thinking through a series of combinations, model issues, features issues, infra, pipeline, data skews. And scale obviously makes everything that much more challenging. It becomes truly becoming a needle in a haystack problem. And at Meta, we're trying to solve for this, looking at observability end to end. We're trying to combine our knowledge from every part of our ecosystem, linear, signals from stats, events, logs. We're creating intelligent algorithms to power anomaly detection and correlation. And we're enabling ML domain-specific analysis, which is all built on a very scalable monitoring infrastructure. Essentially, we want to find that butterfly that flapped its wings a week ago. So summarizing some of the lessons we've learned so far, AI growth is something we need to plan for. Demand is ever growing. Efficiency is going to be critical. Not all ML applications are the same, so we need different data optimizations for different ML applications. Data infra must be redesigned from the ground up, beyond just incremental changes. Investing in enabling faster velocity for model refreshes is valuable. And finally, ML adds exponential complexity to observability. I'm sure these experiences resonate with many of you going through this journey as well, which brings me back to this event. I am thrilled that we'll be diving into some of these topics in the conference. You'll get to hear from an awesome panel of speakers, and I'm also going to be hosting a fireside chat with Jan LeCun, Chief AI Scientist at Meta. It's going to be an exciting conference, so sit back and enjoy these sessions. Thank you.